इंग्लिश में बोलो.
Yep.
Stream started. Yep. Wait a second. Yep. Hello
Yep,
guys.
hello guys.
So today we are reviewing the code for Tornado Cache. So Kunal, Tornado Cache. GitHub. So what have you covered till now, Kunal?
Yeah, like I was learning about Merkle trees and like Z-snark algorithm basically.
ZK
Like,
snark
but still,
algorithm.
like we have to walk again those parts.
Uh-huh. So is this the one we will be reviewing? I'm sending the link on like the meet.
Yeah, yeah, this one.
The core, right?
Yeah.
Okay, let me just clone it. Sucks. Okay, so I will clone it. I will share my screen, Kunal. Like,
Yeah.
no, I think it is better that you like you do it on your own. Like, we'll review the same thing.
Yeah, yeah. Works.
Claude, and I am doing init to initialize. So just a second, I'm running Claude init.
Yeah.
So how do you think we should start reviewing the code? Like, from which contract we should start?
Uh, like from the base, like how the flow goes in this contract.
Yeah. So what contract should we start with?
Tornado, tornado dot sol, I guess.
Okay.
Maybe.
Okay, so we are importing two things. First is re-enter card, and the second is tree with history, which is something that they have made. We won't be looking at as of now, and they have also declared the verifier, which I think should be verifying some kind of proof, which is an interface. So probably another contract, and it takes proof and a list of array of 6 bytes, or like not 6 bytes but 6 elements as input. So this is
Yeah.
abstract contract, so there might be one function that is declared but not implemented, which is process deposit. So I think this should be inherited by somebody else. But let's start with tornado, right? So
It's e tornado is the main contract.
which one? ETH tornado.
Yeah.
Okay, so let's start with tornado.sol, because that'll make more sense, right? So
Yeah.
let's just give like let's just give ourselves a couple of minutes to just understand the architecture itself, right? So just walk through and let me know. Okay,
Yep.
so
Sure.
I have also created Claude file. Okay, should be helpful. Okay, so Coronado contribution. So there is a verifier, there is a denomination which I don't know what it is, nullified hashes, which is a mapping of byte 32 to boolean. Okay, how? So let's do one thing. Let me just put it as my computer uses both of them. Yep. I'll create a Miro board where I am documenting all the structures and the flow. So I'm gonna invite you there. I'll send a link.
Yep.
So first of all, a verifier is a contract. The second thing that I see within tornado.sol is like a variable which is denomination. No clue what it is. There's also a mapping which says nullifier hashes, which is like a byte 32 to boolean. And the commitment is basically we store all commitments just to prevent accidental deposit with the same commitment. No idea what does it mean. We store all commitments just to prevent accidental deposit with the same commitment. Okay, so I think what they are meaning is that like if by any user tries to deposit with the same commitment, they'll just somewhere in the code they'll check whether this byte 32 hash matches like a
Mhm.
previous set within commitments. This is my assumptions.
Yeah.
So uh, let's just understand. Like I'll take a note of this, putting it. Oh my god. This is tornado.sol, right? Tornado.sol. Hmm. The constructor basically. Where is hasher? They are taking hasher, the address of MIMC hash contract, the address of snark verifier for this contract, hmm. the address of MIMC hash contract. I don't have clue on how does ZK works, so this is going to be the first time I'm reviewing anything that is related to ZK. Transfer amount of each deposit. Transfer amount of for each deposit. Okay, denomination means like as far as I know, Tornado splits a single transaction to multiple parties, right?
No.
So how does it work?
So what
Like,
happens
uh huh.
is, like there is like in Tornado Cash, you deposit the funds and you get in a hash or something like a byte or two string,
Mm-hmm.
and like it's just like a mixing thing. So you deposit $100, I deposit $100, some other guy deposit $100. Now we three deposit $100, and we got a receipt like a hash which is unique.
Yeah.
Yeah, which is unique to us, and then we go to like we create another address, uh, and then withdraw from that address. So no one knows who, like which one are us, like which one is me, which one is you, who withdraw $100. So the token get mixed completely.
Yeah.
So
So what I was saying is, I think it's not just. Let's suppose that a user wants to like deposit $100, right? Now he wants to get like $100 to from like to another address. Now what I believe what Tornado will do is like he it's not gonna put like transfer money from a single entity but multiple entities and then send it as a whole to one user, because here they are setting denomination in constructor, which basically means transfer amount for each deposit. So each deposits mean like I'm not pretty sure what does it mean, to be honest, but I think it's going to be batches where multiple batches deposits to a single address. But let's see how does it work. So
Yeah.
we are initializing Merkle tree history with Merkle tree height, which is given by user, and the hasher address. Okay, so constructor is very like initializing verifier and the hasher, which is the hasher, the verifier, and denomination is the okay.
So the nomination is a fixed amount basically. So in Tornado, there is a fixed, like each router which is deployed, like each Tornado cache router which is deployed,
Mm-hmm.
have a fixed denominator. Like it is like, let's just say one address, one Tornado cache address is for 10 ETH, one is for 1 ETH, second is for, like, these are like multiple denominators they have created.
Mm-hmm.
So you can only deposit that particular amount. So you, in one ETH, 1 ETH Tornado cache, this thing, you can deposit only 1 ETH in it simply. That's why like the mixing can be done easier, like somewhat
Uh,
like that.
let's see. So okay, we are in constructor. We are taking verifier address, the address for hasher, the denomination uint which we are setting it to denomination, and then we are taking Merkle tree height and just passing it to Merkle tree history. We let's just we are just slowly looking into it, but in later time we'll just dive into the nitty gritty very closely, right? So for as for now, we are good with the basic understanding. We don't need to actually dive into the code right now, like fully. Let's just go on like overlook them slowly.
Yeah.
So deposit funds into contract. Deposit funds into contract. The caller must send ETH or approve ERC20 value equal to or denomination of this instance. The caller must send for it or approve value to or equal to. I think you are right. Denomination means something like the minimum amount.
Yeah, the maximum amount is just like,
To
it's not
or
minimum.
equal. So they're saying the caller must send or approve value equal to or denomination, yes, of this instance, correct. The maximum value, right?
Yeah, like it's an exact value, not maximum. It's like the
I,
exact
I
value you have.
let's just see. So
Yeah.
we are the commitment node, external payable not in trend. We are checking commitment is not there. Yes, I was right that we did not do that. Insert index. I think insert is in within the Merkle tree history library. Not big. Okay, never mind. Just skip it for now. Um, what
The
was
verifier Merkle tree history are like too complicated things.
sorry? What are you saying?
Like the Merkle tree history and the verifier are like two complicated contracts, which I, because these two main logic of
Yeah,
that.
yeah. Yeah, we are not going to rush. We are going to research like how does it everything works, and we are going to break things out. I am pretty sure that it will be very hard, but let's just do not like overcommit and try to do it faster. Just go slow and with your own pace. So in deposit, we are checking whether this commitment that the user is committing to is not a part of. Uh, not already a part of the mapping of commitments. Then we
Mhm.
are I think we are what does insert does is it leave next index. Merkle is full, there is no leaves that can be added. Okay, so I think it is kind of adding, let's just assume it's just adding commitment to something, to maybe a Merkle tree. Yes, I think to
Yeah.
our levels, current index. Yeah, we are going to learn. I don't know much about Merkle Patricia trees, so we are going to learn about those as well. But yeah, I think we can skip it for now.
Hmm.
Commitment is basically a setting. So once we do something with insert, we are like putting the commitment as true, which is
Insert is just like it just giving you the index on the memory where to keep, because the problem is the like the user can just try to get the stuff, so it just like checks which index in the memory is available right now, not in the memory but in the Merkle tree which is available right now.
yeah, but I don't know much about Merkle trees, so I don't know how it's going to work. But like let's just ignore it for now.
Yeah, yeah.
Okay, so then we are processing deposit and we are emitting. So processing deposit depends upon like whichever contract this is. Uh, this is basically inheriting. So we are just gonna pass it. Withdraw deposit from the contract. Proof is a zk snar proof data and input. Proof is a zk snar proof data and input. And input where the file is input. It's an array and of circuit public input. I don't see input. Okay, never mind. So in withdraw and input is an array of circuit public inputs. Merkle root of all deposits in the contract. Hmm. Okay, let's just pass it the comment. Let's just let me do it here. What does it mean? So
Okay, got.
okay, so we does not should be doing verify. In deposit we are just we are taking the proofs from the user, and then we are also asking for the Merkle root of all the depositors till now, and nullifier hash is unique deposit nullifier hash, the recipient and the relayer, and other details regarding fees and refund. And then we are calling to verify proof, and just uh, nullifier hash, and then setting it to true. But when we did, okay, we did it for commitments. Okay, nullifier is basically once we have processed, then we are putting into that, and nullifier hash and commit. So there are two hashes: nullifier hash, which nullifies the transaction and mark it as done,
No, yeah, like somewhat like that. Yeah.
and then there is a commitment, which is like committing towards a deposit. Is known if root equals to root. Okay, so we are just then processing the payout, and yeah, that's just it for tornado.soul. Now, what is Merkle tree with history? I think let's just first understand like how Merkle trees works, because I think that will make more sense.
Yeah, agree. So, like, you like learning from this thing, or you, or like talks or something, or would you like to have a YouTube video or something?
Let's read the links that you sent were regarding what?
It's like it's not related to Merkle tree. It's like a one step ahead of Merkle tree, which is being used in Tornado Cash.
Mm-hmm.
So Merkle trees are just like they are public things. So the data in them remains public, and to verify it, you need all the hashes in the Merkle tree to verify that your ones is correct.
Yeah, let's learn. Uh, let's run from Cypherin. Okay, let me just open Anara. I'll just import this. Learning web3. Import. Mm.
Yeah, it's just like hash of all the values. It's just like a simple thing. Like you hash everything, and to verify, you just need a root hash simply.
Uh-huh. Yeah. Yeah, but let's understand it deeply, because I think Tornado Cash is majority of the things are related to Merkle trees, and if we go with the broken knowledge of Merkle trees, I think that will be like not ideal.
Agree.
Yep. So I am sharing you the link.
Yeah, I have the Cypherin
Uh,
link. I'm just having the diagram. Like you can look at the diagram. It's like pretty much understandable using the diagram.
yeah, I know the general gist of how it's supposed to work, but let's just understand it thoroughly. So
Yeah,
let's give it. I think it's not too big.
yeah,
Let's give it like 5 minutes, and we can like connect once we both are done.
yep, sure. Okay, so if a tree size is like n, like what Merkle tree solves is like a bigger picture. So in place of storing million data in an array and then checking if the data exists in that uh, in Merkle tree, the data we have to store is just log of the n, log 2 of the n basically. So let's just say if you have 10 lakhs 10 lakhs data, 1 million basically, 1 million data, and to check the Merkle tree you just need 20 hashes to prove that your one exists or not.
Yeah.
Yeah.
Leaves. Proof. Mm. Uh, did you read?
Yeah.
Just give me a second. I have a question that I'm trying to answer. So,
Got it.
okay. Eh, so basically, it's like yeah, the hashing two elements together until unless we reach the end of the hashing cycle, right? And
Yeah.
we for verification we need to pass the siblings, which are
Yeah.
like if like we are there are four leaves, one, two, three, four. If we
Yeah.
want to verify the second, like the leaf 2, then we need to pass the hash of leaf 1 and the hash of 3 4.
Yeah.
Ah.
Like to pass a sibling. So the thing that the benefit of is the Solidity contract itself stores only the
Mm-hmm.
root, which is like the computed hash of every data. So it's just like SHA-256 basically in general terms. If I would say, if you compute a SHA of anything, it would be same every time.
Mm-hmm.
So all the data that we have, if we recompute the data back again, it should be the same hash. It would be the same root hash simply. So that's the logic they have following, and the benefit is the Solidity contract is just storing the root hash. We are passing the leaf nodes, and the point is we just like the iteration it goes under to check is only log n basically of the number of items we have simply.
Mm-hmm. Yeah.
They, like
So
there is
let's suppose that there are 40 elements, okay? 40
yeah, there
leaves.
example. I shared you the image. If you open it, so it's showing around 9, 10, 11, 12, 13, 14, 15, 15 data
Mm-hmm.
basically.
Yeah.
So over there, if you see, let's just say you want like you are verifying like L4 is your data.
Mm-hmm.
At L4 it's your data. So for to verify L4, you need L4 and L5
Mm-hmm.
hash basically.
No, we need to pass. Yeah, we need to do that, but we need to pass siblings. So
Yeah,
yeah. We need to pass L4 and L5. Yes.
and so the sibling of L4 is L5, so you pass it. Then we hash it, and then we got we have to also pass V6 and V7 hash, the hash of V6 and V7. Then we have to pass the hash of V0, V1, V2, and V3 hash together. And at the top, like we have to pass the rest of the hash. Like it's just like we just match that thing again simply.
So we need to pass all the leaves, right,
Yeah,
as proofs,
yeah.
or just the L4 and L5.
Like for this particular one, you will pass L4 L5 hash of L4 L5.
Uh-huh.
At the next level, we pass hash of 4
No,
5.
no. That is the that that will be automatically done. Let's suppose that we want to know that let's say कि V5 is a part of this Merkle tree or not. So what we'll do is like V5, for V5 we need to give V4, right? So V5 and V4 we need to give, right, itself.
Yeah.
So they'll like compute themselves.
No. So the thing is, uh, we have L4 with us. Then
Mm-hmm.
we want to verify. So we have L4, we have L5.
Mm-hmm.
We hash them. Then we move one way up. Then we already have the hash of 6 7. We are not computing it back. We already have the hash of 6 7. We just hash it with 4 5. Then moving forward, we already have the hash of 4 5 6 7, which we already computed previously.
Like how do you, so if the contract, see, let's say there is some data which is saved, right? How would the user have the data of other elements? Only he needs to verify whether I am a part of this, let's suppose airdrop, right? So
Mhm.
what he can just give the data for his himself, he doesn't know all other entities, so how he's going to give all the leaves?
It's not all the leaves. It's just like the leaf nodes,
Adjacent.
adjacent ones.
Hmm. Yeah, like I am confused here, but just give me a second. I'll just try to understand it one more time.
So like in airdrop and the stuff, like the website itself, which is hosting this thing, stores the whole Merkle tree within it.
Uh,
So the project will construct an off-chain Merkle tree, and the contract will just have the root hash simply.
yeah,
So
they
it's
need to update themselves.
yeah, they will create an hash and then update it on the contract. The root hash would be updated on the contract, and the hash tree would be updated on the backend or someplace simply. So just like a program which is fetching all the root leaves and the stuff.
Wait a second.
That's why this ZK snark picture comes in, because the data is public, the whole Merkle tree is public. Then who deposited the amount is also public.
Yeah,
That's
let's.
why
Mhm.
that's ZK snark algorithms comes in the picture to hide those things. Who deposited and who withdraw it. Like you don't know who withdraws it. Withdraw it's basically.
Mhm. Okay, so we need to pass just adjacent hashes, right? But wait a second. How would wait? Um, hmm, second. Yeah. Okay, so ठीक है. Let's proceed now. So we know how Merkle trees are supposed to work, right?
Mhm.
So we have gone through tornado.sol. So we now get the idea like how it's working. But now we need to understand what are like the proofs. Proofs. I think proofs will be here. The proofs will again be the adjacent. Similar to what we learned, the adjacent leaves, right? And the root is similar, that they need the Merkle root, Merkle tree root basically. And Let's see how it's working. The main logic resides in verify proof. So
Yeah.
let's read verify function verify proof. Proof is valid given the hard coded verifying key. So it accepts two things. One is proof and the second is input, which is like six elements of event, which is and six elements are basically the root, the the nullifier hash, recipient, layer, fee, and refund. Okay,
Hmm.
and then thing is we are decoding proof into 8 u into 56 array. What is Yep, so I am trying to understand the logic behind how does verify proof work. So there is a lot of maths. So
Hmm.
let's like I instructed AI with the study prompt uh, to explain me how does verify proof works. So I am just going through how it's going to work. So quick the first thing that AI has asked me is like how comfortable I am with ZK Snark basics like proof elements ABC and public inputs and solidity, right? So I am comfortable solidity but no idea about ZK Snark. If functions are taking proofs, given 6 returns below. Given a ZK snark proof, SIG public decide if proof is valid. Quick question: does public inputs term make sense? They are known values. The verifier checks against. So, public inputs are basically what? Public inputs are basically where was it? The root, which is I think it's saved within this. A second. Where um the root. Okay, never mind. So root is there, nullifier hash is there. No, then so the nullifier hash is public. Nullifier hash basically nullifies. Uh, I think it nullifies.
Nullifier is not public.
What do you mean not public?
So there is the hash of nullifier plus secret, which is public.
Nullifier hash is public.
No, no, nullifier plus secret hash is public.
No, nullifier hash is basically the mapping name within Tornado cache.soul. Tornado.soul.
Yeah, it's just like it accepts and withdraw, but while you're depositing, you are just putting the nullifier plus the secret in a hash format. And then when you are withdrawing, that nullifier is just there to prevent double withdrawal from any user. So this nullifier hash will check with the verifier, like the ZK snark verifier, to verify those things.
Yeah, but the AI is saying that the inputs that are the public data, for example, root, nullifier hash, recipient, relay, refund, and fee, are all public details.
Yeah, like these are public details from the withdrawal,
Mm-hmm.
not from the deposit side. At the time of deposit,
Yeah.
no one knows what is nullifier is,
Yeah.
unless
The only thing that it requires is commitment, and don't know how commitments are generated.
commitment. Just check the comments just above that. Like it says, which is like Presidian hash of nullifier and secret.
Mm-hmm.
So it's just hash of nullifier and secret. There is some sort of hashing mechanism it's being used here.
Yeah. So, but so nullifier is not public. You are saying, right?
Yeah, it's not public at the time of deposit, but at the time of withdraw, we ask it from the user.
Yeah.
We need to learn about this snark thing, like what exactly it is. Okay, there is a specific requirement and specific feature of Presidian hash. That's why it's being used. So I'm sharing you this thing on the chat. So these hashes, these are like multi-way computed. So like the Presidian hash of A plus Presidian hash of B is equals to the hash of both. So at the time of deposit, we give a hash of both, and at the time of this thing, we are giving the hash of this thing. Things divided in equal format, then we are getting it match or something like that.
Let's see. Okay, so when you are depositing now, then you are actually passing one thing into the Merkle tree, which is the Pedersen hash of nullifier and secret. and that's being deposited into the Merkle tree. Now, when you do withdraw, uh, the proofs that you pass as an input shows that, like, signifies that you have an leaf, and you know the private nullifier of it, and you publicly reveal the public nullifier hash, and then you can track. Yeah, okay. So so when you are trying to, so in order to withdraw, you need to know the nullifier hash. Basically, it shows like everybody that you are showing this as a proof that I know this secret to unlock this particular leaf. It's like something similar to this.
Hmm.
And there is a difference between nullifier and nullifier hash.
Yeah, like nullifier hash is just hash of nullifier.
Yes.
It is hash of nullifier.
Yes. And basically we are, so there was a mapping of nullifier hashes, not nullifiers. Okay, so we do is known. Okay. Proof.
Got it. So I'll tell you.
Wait. Huh, yes.
Yeah. So, like, can you share the Miro board or something like which you're saying? I just, or else like if you are on the code itself, I'll just pinpoint you.
Wait, I'm sharing. Sending on Google Meet. Done.
Mhm.
Yeah, so Hmm. This includes a lot of maths.
Yeah. This verify itself is like last complicated thing I'm stuck on. How exactly it is verifying that thing. Like rest of things is like pretty much clear to me. Like how thing works, how deposit works, how withdraw works, how like the security is there, like which is preventing it the thefts and the stuff. It's just like how does this nullifier hash is proving, like this proof and this nullifier hash is proving that this is the correct owner and this is like the user, valid user.
Mm-hmm.
I have pasted a like flow also on the board,
Yeah.
still verifying that the function itself, how it goes. If you got it, let me know and please explain. Hmm, I'm still
Okay. So I asked AI.
uh,
Wait a second. So
okay, got it. It's a proper math in this.
added sources that will help us to learn the maths behind this. So we
Mhm.
need to understand. We need to read a lot.
Yeah, we need to verify ourselves. It's just like this is the final pit stop for us.
This is a reminder. Sleep. This is a reminder. Sleep.
Okay. Okay. Let's continue tomorrow. Uh,
Yeah.
I think we have done. We have covered. We have learned some bits. So far, we have in this stream we learned about how uh,
Merkle trees.
yeah, Merkle tree works and little bit about Tornado Cache. So the task for tomorrow is basically get understanding of what zero knowledge proofs are,
Yeah.
and let's understand epileptic curves as well,
Yeah.
and then we'll go into the heavy lifting of algebra. Okay. Okay, and then I'll see you tomorrow. Bye bye.
Yeah. Bye.
Arey